Look at a modern skyscraper. When a building climbs 150 stories into the air, the physical scale alone is difficult to comprehend. But underneath that reflective glass and polished concrete, the true strength of the structure relies entirely on a hidden internal skeleton made of millions of steel reinforcing bars, known as rebar. To reach these heights, engineers rely on a mathematical system that organizes this dense web of metal into a rigid, predictable lattice. Before a megastructure can conquer the sky physically, it has to be conquered mathematically. Go back a few decades to the estimation era of civil engineering, when buildings were relatively small. Engineers calculated the amount of steel they needed using rough manual estimates. The entire industry relied on a set of standard recommendations created by Professor Detta. His formulas became the universal handbook for estimating steel quantities. These rules of thumb were effective as long as the structures remained short and structurally simple. But those estimates broke down under pressure. When engineers needed to pack multiple steel bars into a single concrete pillar to support taller, heavier loads, the old formulas simply could not provide accurate values. You cannot build a 150-floor tower based on a rough guess. A tiny mathematical rounding error at the foundation compounds as you move upward, increasing the risk of structural failure at the top. Think about a single concrete pillar at the base of a high-rise. It has to bear an immense structural load. This diagram shows a cross-section of that concrete column. To support immense weight, engineers must cram exponentially more steel bars into the exact same footprint. Guessing the geometry of these densely packed overlapping bars causes physical clashes inside the concrete and inaccurate steel orders. As modern architecture demanded taller and heavier buildings, the physical ambition of structural engineers outgrew the mathematical tools they were using. To build higher, the civil engineering industry moved toward a data-driven system of precision. That solution is the bar bending schedule, or BBS. BBS functions as a comprehensive digital and mathematical blueprint of modern accuracy. BBS maps a single curved piece of rebar, replacing rough estimates by calculating precise cutting lengths, concrete cover, and bend deductions. By generating exact geometries, BBS solves structural density. Hundreds of bars within a single column fit perfectly, without a single structural clash. BBS acts as the critical, invisible data system that prevents these massive steel skeletons from collapsing under the weight of their own complexity. Back out in the physical world, coordinating a 150-story megastructure under construction requires this exact level of certainty. The precise data generated by the bar bending schedule pairs with modern construction equipment and advanced site techniques to ensure the assembly matches the design. Managing these immense volumes of steel moving thousands of feet into the air is a significant logistical challenge. The bar bending schedule makes that process manageable, accurate, and safe. By transforming millions of physical steel pieces into a strictly managed information system, BBS provides the logistical framework necessary for high-rise construction at this scale. For the civil engineering profession today, this level of precision is the baseline. Because of the immense physical demands of high-rise construction, the manual estimation methods of the past are obsolete on modern sites. Mastering the bar bending schedule is a foundational requirement for any site engineer or fresher stepping onto a construction site. Every 150-story skyline is a testament to the bar bending schedule, the system of mathematical accuracy that allows us to build into the sky.